We consider a finite group and we denote by M the number of conjugacy classes, and we denote by P the number of non-equivalent irreps of this group. We already know there are only finitely many non-equivalent irreps. And now we have this character orthogonality, which we wrote like this. There's a sum over the conjugacy classes, so the C here runs from 1 to M, and then we have the characters here in representation J and an irrep K, and we have orthogonality. Now let's rewrite and reinterpret this. So fix for a moment the J and then collect these characters, the numbers chi cj, in a vector. So how many components does this vector have? As many as there are C's, so that's the number of conjugacy classes. So it's a vector in Cm. Now, how many of these vectors do we have? There are P vectors of this kind. Since now we can vary the J's from 1 to P. And they are all mutually orthogonal again. Because that's what this relation here says. This is like, it's not quite the canonical scalar product. There is some weight here, the number of elements in the class. But we have orthogonality with respect to this scalar product here. So if there are P mutually orthogonal vectors, then the dimension of this space has to be at least P. So P is less than or equal to M. That's what we can conclude here. And that's what we can immediately show with character orthogonality. And if we put in a little bit more work, and you will do this in the exercises, then you will see that here again we actually have equality.